Okay, starting with this problem, which is a Diels-Alder reaction, we see our diene on this side, and we see our dienophil on this side, which I'll just indicate with a P, even though it doesn't start with a P, but just as a way of differentiating between the two of them. Now, I've watched a lot of videos on these reactions and have learned quite a bit about them, and I've seen people draw them in a couple different ways. But one way that was actually linked in our module, I believe, is by organic chemistry tutor. And he draws it like this, where we have the double bond coming right here. And then, sorry, I'm not very good with this pencil on my laptop, coming right here. And then we have here coming this way. Okay. So I have found the easiest way to keep our organization is to number our carbon. So let's do that now. We have 1, we have 2, we have 3, and we have 4. That is on our diene. On our dienophil, we'll make this 5, and then this number 6. So we now have our new 6-membered ring. Let me just draw that out real quickly. And again, I apologize that I'm not the best with this pencil on a laptop mouse. It definitely makes it more difficult than if you were using an iPad or something like that. Now remember, we had this movement of the double bond right here, so we'll have our double bond here. And the other 2 pi bonds were used to make new sigma bonds that made this 6-membered ring. Now remember, we have our number 6 right here and number 5 right here. To keep track of these, this is number 5 and this is number 6. If we recall, our number 6 has an ethyl coming off of it. So let's just draw that. And let me draw that actually a little better, because that was a very poor attempt at drawing an ethyl. And we will do stereochemistry. I'm just drawing it for simplicity's sake right now. Here, number 5, we had our methyl, as you can see right here. All right, so we now have our basic structure put together. We have our diene and our dienophil that come together to make a 6-membered ring. We have our double bond in the right spot. Our other pi bonds were used to create new sigma bonds that brought the 2 reactants together. We have our ethyl, which is now over here. And we have our methyl right here, which is now in the correct spot over here. Now let's talk about stereochemistry for a moment. Now, one thing we'll notice is that these are cis to each other. You can see that right here. So whatever happens to one is going to happen to the other, and it can be attacked from the top or the bottom. So if I remove this ethyl and methyl for a moment, and let's also get rid of this 5 and 6 just for drawing simplicity's sake. We could draw this on a dash with our ethyl. And here's our methyl. Or we can also draw it on a wedge. The pen drawing is a little messy. So we're looking for an answer that looks something like this. 2 different versions, one on a dash, one on a wedge, one is an ethyl, one is a methyl, and that will be our answer. So let's go ahead and scroll down and see if we can find an answer that reflects this. All right, our first choice, let me just pause and clean this up for a minute to make it easier on us to see. Okay, and we're back. I just cleaned up some of that extra stuff we don't need. We're just looking for products that look like this. And if we scroll down here, answer choice A, you know what? Somehow I accidentally erased my double bond right here. So let me put that back. Answer choice A looks very, very similar to what I drew right here. You can see our six-membered ring. You can see our pi bond or double bond. You can see the ethyl and you can see the methyl. And you can see that they are represented, one on a wedge and one on a dash, which is similar to ours, except for we did the dash first and the wedge second. So this is looking pretty good right now, A. We'll choose that, but we'll also keep looking to make sure nothing else pops out at us. Our next one down is similar to what we drew, except for we have one on a dash and one on a wedge. We have our methyl on a wedge and our ethyl on a dash. That is not correct. They would both be on the same. Going C, it's just the opposite of B. The ethyl is on a wedge and the methyl is on a dash. That's not correct. And D, again, same deal, same as C, except for we lost our double bond. So the correct answer choice is A, but let's make sure that the system agrees with us. Let's click check answer, scroll up, and that is, in fact, the correct answer. We got it right, and we'll move on to the next problem. Okay, moving on to our next problem. Our last problem was a Diels-Alder reaction, and this one is a 1,4 addition reaction. So we're a little different. And as I zoom in here, my eyes are immediately drawn to the NaCN, and we know that Na is a spectator ion. So we'll go ahead and give our CN a negative. We also see that this is done in an acidic environment. HCl is a strong acid, so let's just mark this with an A to tell us that this is an acidic environment. We also know that whenever we have an oxygen nearby, it's going to be pulling quite a bit of electron density towards it because it is a very electronegative atom. And the consequence of which is we're going to have positives, partial positives, on our carbons that are nearby. So if we count this right here as carbon 1, this is carbon 2, and this is carbon 3, carbon 3 will have a partial positive. And that will give an opportunity for our nucleophile to come and attack. And what's going to happen is that's going to allow the CN to attach right here. Now our double bond's not too happy anymore because we have our CN attached, so that is going to move right here. And as a consequence, our pi bond is going to move up here. So our intermediate will look something like this. Very poorly drawn, but I think you get the point. And we have our O up here, which has a negative charge because it now has the 6 electrons, lone pairs, I should say. So let's not forget that negative charge right up there. Now, don't forget, we are in an acidic environment. So one of these lone pairs is going to come over and it's going to go ahead and nab one of those hydrogens. And that's going to lead to something that looks a little bit like this. Okay. And this right here is called the enol form of our product. Okay. But as we learned with Dr. Kerr last semester, there is some tautomerization that can happen here that would create the keto form, which in this case is more favorable. And that would look like this. And as a reminder from last semester, when Dr. Kerr talked about the hydrogen being lost, she always loved to point out that almost every solution is going to have a little bit of water in it. And what will happen a lot of times is the water will come along, grab that extra hydrogen, and it will turn it into H3O plus. This is one of her favorite examples, and it definitely stuck with me. Okay. So I haven't had a chance to look at the answers yet below, but it's going to be one of these, depending on whether it wants the enol form or the keto form. Considering keto is a little more stable, it's probably going to be keto, but let's take a look. We'll go ahead and zoom out here. And just like the last video, I'm going to pause for a second and get rid of some of this just to make it easier on us. Okay, now it's a little clearer to see. It's not quite as much stuff there. Let's see which answer aligns with ours. So A is similar to our keto form. It has the double bonded oxygen, but it's missing, it's missing the fact that the CN should be down on C3, not C2. So A is wrong. B, oh, you know what I'm realizing? When I was copying it over, I just forgot to put the CN here. I apologize. We can fix that though. Now we have the CN. Okay. And this does look like our keto form. As you can see, this is a direct copy of that. And I didn't notice that when I was switching, when I was tautomerizing from our enol to our keto. I just forgot to make that copy, but it is the same thing there. So I think B is going to be our answer. But let's keep going. C puts the CN at the tertiary location, or what was once tertiary, which isn't like an unreasonable thing to think, because if we consider that our oxygen is pulling electron density away, it wouldn't be unreasonable to think of the carbocation here, but in our 1,4 addition reaction, that just doesn't happen. So we know that this is wrong. And in D, we have an NH, which is totally wrong. So B is definitely the right answer, in my opinion. Let's go ahead and see if the system agrees. And it does. Correct answer. Sweet. So we did get that one right. All right, I think I am running out of time here, but thank you very much for watching my video. I appreciate you sticking along with me. I look forward to talking to you next week.